Android platform overview. We shift from pure Kotlin to Android development. Android is a mobile operating system with its own architecture, components, and development model. Today we understand what Android is and how applications fit into the platform. Android is a Linux-based operating system. It runs on phones, tablets, watches, TVs, and cars. Billions of devices worldwide use Android. Android is open source. The core platform is maintained by Google. Device manufacturers customize it. As a developer, you write applications that run on Android. The platform provides services your app uses: UI, storage, networking, sensors. Android handles security, resource management, and lifecycle. Your app operates within the platform's rules. Android is built in layers. The Linux kernel sits at the bottom. It manages hardware, memory, processes, and security. Above that, the hardware abstraction layer lets the platform talk to specific devices. Camera, GPS, sensors, native libraries, and the Android runtime provide system services. Graphics, database, media codecs. The application framework gives you APIs. Activity management, content providers, notification services. Your application sits at the top. It uses the framework to interact with the system. Android apps are built from 4 types of components. Activities are screens. They provide user interface. Users interact with activities. Services run in the background. They do work without UI. Music playback, syncing data. Broadcast receivers respond to system-wide events. Battery low, incoming call, airplane mode. Content providers manage shared data. Contacts, media files, app databases accessible to others. Most apps primarily use activities. Services and receivers handle background work. Content providers are less common. Your Kotlin code compiles to bytecode that runs on the Android runtime. Dart. Android runtime executes applications. Each app runs in its own process with its own instance of art. R uses ahead-of-time compilation. When you install an app, it compiles to native code. Faster execution at runtime. Garbage collection handles memory, like JVM, but optimized for mobile. Smaller devices. Limited resources. Your code feels like regular Kotlin or Java. The runtime handles the translation to run on the device. Each Android app runs in its own process. The process is isolated. Your app cannot directly access another app's memory. Security by isolation. When you start an app, Android creates a process. The app's components run in that process. Android can kill processes when resources are low. Background apps get killed first. Your app must handle this. The main thread handles UI. Never block the main thread. Use background threads or coroutines for long operations. Every Android app has a manifest file. Android manifest.xml declares your app to the system, what components it has, what permissions it needs. Activities must be declared in the manifest. Services, receivers, and providers too. The manifest declares the app's package name. This uniquely identifies your app on the device and Play Store. Minimum SDK version, target SDK version, required features. The manifest tells the system what your app needs. The system reads the manifest to know how to launch and manage your app. Apps need permission to access sensitive resources. Camera, location, contacts, microphone. Users must grant permission. Declare permissions in the manifest. Users permission Android.permission.camera. Some permissions are granted at install. Others require runtime approval. The user sees a dialog and chooses. From Android 6 onwards, dangerous permissions require runtime requests. You ask, the user decides. Respect user privacy. Only request permissions you need. Explain why you need them. Android development uses Android Studio. You write Kotlin code. Define UI in XML or Compose. Configure the build with Gradle. Build produces an APK or app bundle. This contains your code, resources, and manifest. Install on a device or emulator for testing. The emulator simulates various devices. Debug with Android Studio. Inspect logs, set breakpoints, profile performance, Release through Google Play Store. Sign your app. Upload. Users download. Let us summarize. Android is a Linux-based mobile OS with layered architecture. Apps have four component types: activities, services, broadcast receivers, content providers. Each app runs in its own isolated process on the Android runtime. The manifest declares components and permissions. Permissions protect sensitive resources. Request only what you need. Android Studio provides the development environment. Activity lifecycle. An activity is a screen in your app, but screens come and go. Users navigate, rotate devices, switch apps. Android manages your activity through a lifecycle. Today we understand that lifecycle and how to work with it. An activity represents one screen. When users open your app, they see an activity. They interact with its UI. Each screen in your app is typically an activity. Activities are independent. One activity can start another. They can pass data between them. The system manages activities. It creates them, destroys them, pauses them. You do not control when this happens. The system does. Your job is to respond correctly. When the system creates your activity, set up the UI. When it destroys, clean up. Android calls specific methods as the activity moves through states. OnCreate is called when the activity is created. Initialize your UI here, only called once per instance. OnStart is called when the activity becomes visible. Not yet interactive, but visible. OnResume is called when the activity starts interacting with the user. Fully visible and active. OnPause is called when the activity loses focus. Another activity is coming. Still visible but not interactive. OnStop is called when the activity is no longer visible. Another screen covers it completely. OnDestroy is called when the activity is finishing. Clean up resources. The lifecycle flows through states. Launch, OnCreate, OnStart, OnResume. The activity becomes fully active. Navigate away, OnPause, OnStop. The activity goes to background. Return, OnRestart, OnStart, OnResume. Back to foreground, finish, OnPause, OnStop, OnDestroy. The activity is done. Each transition triggers callbacks. Your code runs in response. Not all transitions are smooth. The system might kill your activity. You must handle unexpected destruction. OnCreate, set content view, initialize UI components, restore, save state. This is your setup. OnStart, start operations that should run while visible. Register listeners. OnResume, start operations that should run while active. Resume animations, acquire exclusive resources like camera. OnPause, release exclusive resources, pause animations, save lightweight state, keep these fast. OnStop, save persistent state. Release resources not needed when hidden. OnDestroy, release all resources. Unregister all listeners. This is your final cleanup. When configuration changes, the activity is destroyed and recreated. Rotate the device, configuration change, language change, configuration change. Dark mode switch, configuration change. The system destroys the activity, then creates a new one. Your activity must handle this. OnCreate is called again. Your UI must reinitialize, but you want to keep user state. This is why state saving matters. The user was filling a form. Rotation should not lose their input. OnSaveInstantState lets you save state before destruction. Override fun OnSaveInstantState outstate bundle. Put values in the bundle outstate.put string key value. The system passes this bundle to OnCreate when recreating. Saved instant state is null on first creation, non-null on recreation. In OnCreate, check if saved instant state is null. On recreation. In OnCreate, check if saved instant state is not null. If so, restore your state. Keep save state small. Only save what is needed to restore user experience. Large data should be in a ViewModel or database. You can restore state in OnCreate or OnRestore instant state. OnCreate if saved instant state not null. Restore values. OnRestore instant state is called after OnStart only when there is state to restore. Both approaches work. Choose based on your needs. Most developers use onCreate. For UI components like edit text, the system automatically saves and restores text. You only need to give the view an ID. For custom state, you save and restore manually. Modern Android provides lifecycle-aware components. Lifecycle Owner and Lifecycle Observer let components respond to lifecycle events automatically. View models survive configuration changes. They hold UI state across rotations. Live data and state flow are lifecycle aware. They only update active observers. These tools reduce manual lifecycle management. Less coding callbacks, fewer bugs. We will explore these in later videos. Let us summarize. Activities are screens with a managed lifecycle. Lifecycle callbacks let you respond to state changes: on create, on start, on resume, on pause, on stop, on destroy. Configuration changes destroy and recreate the activity. Save state in on save instance state, restore in on create or on restore instance state. Use lifecycle aware components to simplify management. Respect the lifecycle. Initialize at the right time. Clean up at the right time. Views and layouts. Android UI is built from views. Views are the building blocks of what users see and touch. Layouts arrange those views on screen. Today we understand the traditional view system that has been the foundation of Android UI. The UI is a tree of views. A view is a single UI element, a button, a text field, an image. Each view draws itself and handles its own touch events. Views are organized in a hierarchy. A parent view can contain children. Children can contain their own children. At the top is a root view, usually a layout container. It holds everything else. The system traverses this tree to measure, layout, and draw the UI. First it measures each view, then it positions them, then it draws them. Android provides many built-in views. Text view displays text, the most basic view. Button is a clickable element. Users tap it to trigger actions. Edit text accepts text input. Users type in it. Image view displays images from resources or network. Recycler view displays scrolling lists. Efficient for large data. Each view has properties. Text content, color, size. You configure them in XML or code. Views handle events. On click for buttons. On text changed for edit text. Layouts are view groups that arrange children. Linear layout arranges children in a line. Horizontal or vertical. Children go one after another. Constraint layout positions. Children using constraints. Child A is to the right of child B, aligned to parent top. Flexible and powerful. Frame layout stacks children on top of each other. Simple overlay layout. Relative layout positions children relative to each other or parent. Similar to constraint layout but older. Choose the layout that fits your needs. Constraint layout handles most cases efficiently. Define layouts in XML files. Files live in res/layout directory. Activity askmain.xml for main activity. XML declares the view hierarchy. Parent element contains child elements. Attributes, set properties. Linear layout orientation vertical contains text view and button. The XML mirrors the hierarchy. IDs let you reference views in code. Android:ID equals at plus ID/myButton. Use the layout in activity. Set content view r.layout.activity, not separate structure from logic. Designers can edit layouts without touching code. Views have attributes that control appearance and behavior. Layout width and layout stir height control size. Match the parent fills the parent. Wrap ASCII content fits the content. Padding is space inside the view. Margin is space outside the view. Margin is space outside the view. Text attributes, text size, text color, text content attributes are set in XML or code. XML for static values, code for dynamic changes. Linear layout arranges children sequentially. Orientation vertical stacks children top to bottom. Orientation horizontal places them left to right. Layout Zucker weight distributes extra space. Weight 1 on each child makes them equal size. Different weights give proportional sizes. Layout Zucker gravity positions a child within its space. Gravity centers within its space. Gravity centers within the view. Linear layout is simple and intuitive, good for rows and columns of items. Nested linear layouts become inefficient. Prefer constraint layout for complex UIs. Constraint layout positions, views using constraints. Constrain a view to another view or to the parent. Left to left of parent, top to bottom of sibling. Each view needs enough constraints to determine position. At least one horizontal and one vertical. Chains group views together. Spread chain distributes them evenly. Guidelines are invisible lines for alignment. Positioning available. Constraint layout is flat. One level, many children. No nesting needed. Better performance. The layout editor makes visual editing easy. View binding generates code to access views safely. Enable in build.gradle. View binding true. For each layout, a binding class is generated. Activity main binding for activity nasquo main.xml. In activity, binding equals activity main.inflate layout inflator. Access views through binding the nullsafe, 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 compile time checked. View binding is the modern way to access views. Let us summarize. Views are UI elements organized in a hierarchy. Common views: text view, button, edit text, image view, recycler view. Layouts arrange views: linear layout, constraint layout, frame layout. Define layouts in XML. Use attributes to configure views. View binding provides type-safe view access. The view system is the traditional Android UI approach. Next, we will see Compose, the modern alternative. Jetpack Compose Basics. Compose is Android's modern UI toolkit. It replaces XML layouts with Kotlin code. Instead of describing UI structure, you describe what you want to see. Today, we learn the fundamentals of Compose. Traditional Android UI is imperative. You have views. You call methods to change them. Text view.setText new value. You tell the system how to update. Declarative UI works differently. You describe what the UI should look like for a given state. The framework figures out how to achieve that. If count is 5, show text count 5. If count changes to 6, the framework updates the text automatically. You declare the desired result. You do not write the update logic. Declarative is often simpler, fewer bugs from forgotten updates. The UI always matches the state. In Compose, UI is built with composable functions. A composable function is marked with @composable annotation, @composable fun greeting. Inside, you call other composables to build UI. Composables describe UI elements. They do not return views. They add elements to the composition. You can call composables from other composables. Build complex UI by combining simple pieces. Composables can take parameters, @composable fun, greeting name string, customize behavior with inputs. The framework calls your composables when state changes. It figures out what UI needs updating. Text displays text on screen. Text hello world. A composable that shows a string. Text parameters. Text is the content, color, font size, font weight, customize appearance. Text equals greeting, font size equals 24.sp, color equals color.blues tableas. Respects user font size preferences. Text is the equivalent of text view in Compose. Button is a clickable element. Button on click equals brace action close brace. Text click me close brace. Button has two parts. On click is the lambda for click handling. Content is what the button displays. The content is a composable, usually text, but can be anything. Icon, row with icon and text. Button handles touch feedback automatically. Ripple effect, disabled state, mathematically, ripple effect, disabled state. Column arranges children vertically. Column brace, text first, text second, text third, close brace. 3 texts stacked top to bottom. Row arranges children horizontally. Row brace, text left, text right, close brace. 2 texts side by side. Column and row are the compose equivalents of vertical and horizontal linear layout. They take parameters for arrangement and alignment. Vertical arrangement, horizontal alignment for column. Arrangement. Space between spreads children out. Alignment. Center horizontally centers them. Modifiers change appearance and behavior. Text x equals hello, comma modifier equals modifier.padding16.dp. Modifiers are chained. Modifier.padding8.dp.background_color.gray.fillMaxWidth. Order matters. Padding before background adds padding inside the background. Background before background adds padding inside the background. Background before background adds padding outside. Common modifiers: padding, size, fillMaxWidth, fillMaxHeight, background, clickable, border. Modifiers are the primary way to style composables. Instead of many parameters, composables take a modifier. Box stacks children on top of each other. Box brace image content alignment equals alignment.center brace text overlay close brace close brace. Box is the compose equivalent of frame layout. Use content alignment to position children. Alignment.center alignment.bottom end. Children draw in order. First is bottom, last is top. Box with modifier.fillMaxSize is a common pattern for full screen content. Preview lets you see composables in Android Studio without running the app. At Preview at Composable, Fun Greeting Preview Brace, Greeting Android Close Brace. The preview annotation tells Android Studio to render this composable. You can have multiple previews, different states, different themes, different sizes. At preview show background equals true, name equals light mode. Preview functions do not ship in your app. They are for development only. Preview speed up development. See changes instantly without building and running. A simple compose screen combines these elements. At composable fun profile screen column modifier, fill max size padding 16dp brace, text name, font size 24, specs email button on click brace close brace, text edit profile close brace, column arranges elements vertically. Text shows name and email, button triggers an action, and the entire UI is Kotlin code, no XML, no find view by ID, no binding classes. Compose is concise, type safe, and reactive. State changes automatically update the UI. Let us summarize. Compose uses declarative UI. Describe what you want, not how to update. Composable functions build UI. Mark with add composable, basic composables, text, button, layout composables, column, row, box, modifiers, style and position elements. Chain them together. Preview annotations shows composables in Android's GUI. Compose is the modern way to build Android UI. State in Compose. Compose UI reflects state. When state changes, the UI updates. This is the core of declarative UI. Today we understand how state works in Compose and how to manage it effectively. In declarative UI, you describe what the UI should look like for a given state. State is data that can change, a counter value. A text field's content, whether a checkbox is checked. When state changes, the UI rebuilds. Compose calls your composable functions again with the new state. They produce new UI. You do not manually update the UI. You change the state. Compose handles the update. This is powerful. The UI is always consistent with the state. No bugs from forgetting to update some part. Consider this. var count equals 0 in a composable. Button increments count. Text shows count. This does not work. The variable is recreated every time the composable runs. Changes are lost. Composables can run many times. Anytime state changes, Compose might call your composable again. Local variables do not survive. You need a way to keep state across recomposable again. Local variables do not survive. Local variables are not enough. Remember, preserve state across recompositions. Val count equals, remember, brace mutable state of 0, close brace. Remember, tells compose, keep this value. Do not recreate it on recomposition. Mutable state of creates observable state. When it changes, composables that read it recompose. Together, remember, plus mutable state of is how you hold state in composables. The value survives recomposition. It does not survive configuration changes or process death. Mutable state of creates a state holder. It wraps a value. You can read and write through it. Val state equals mutable state of initial. State.value gives you the string. State.value equals new changes it. When you write compose knows, it schedules recomposition for any composable that read this state. This is reactivity. Change the state. UI updates automatically. Writing state.value everywhere is verbose. Kotlin property delegation helps. var count by, remember, brace mutable state of 0, close brace. Now count acts like a regular variable. Count gives you the value. Count equals 5 changes it under the hood. Delegation calls value getter and setter value. Getter vow delegation calls value getter and set value from compose runtime for this syntax. Recomposition is when compose calls your composables again. It happens when state changes. Compose detects the change and reruns affected composables. Compose is smart. It only recomposes composables that read the change state, not the entire UI. Composables should be fast. They run often. Do not do heavy work inside composables. Side effects in composables can cause problems. Remember, composables might run many times. State hoisting lifts state up to a caller. A composable receives state and an event callback. It does not own the state. At composable fun count int on increment arrow unit. The composable displays count. It calls on increment when clicked. The parent owns the state. It passes count and handles on increment. Why hoist? Reusability. The composable is stateless. It works with any state source. Stateless composables are easier to preview, test, and reuse. A stateful composable manages its own state. At composable fun counter brace var count by remember dex count button increment close brace. It is self-contained, easy to use, but harder to test and reuse. A stateless composable receives state from outside. At composable fun counter count in increment brace close brace. It is controlled by the caller, more flexible, more testable. Best practice, make composables stateless when possible. Hoist state to the level that needs it. A form with text input. The parent screen owns the state. var name by remember mutable state of empty. The input receives name and on-name change at composable fun name input. Name string on-name change arrow. Unit brace outline text field. Value change on-name change arrow unit brace. Outline text field value equals name on value change equals on-name change equals brace. The parent composes the input. Name input name on name change equals brace. State is hoisted. Input is stateless. Easy to preview, test, and reuse. Let us summarize. State drives compose UI. When state changes, UI recomposes. Remember, preserve state across recompositions. Mutable state of creates observable state that triggers recomposition. State hoisting lifts state to callers for better reusability. Stateless composables are easier to test and reuse than stateful ones. Design composables to be stateless where practical. Hoist state to the appropriate level. Navigation. Apps have multiple screens. Users move between them. Navigate forward to see details. Navigate back to return. Today we understand how to handle navigation in Android, both in traditional views and in Compose. Navigation is moving between destinations. A destination is a screen or content the user can reach, a home screen, a detail screen, a settings screen. Navigation forms a graph. Destinations are nodes, transitions are nodes, transitions are edges. Users traverse this graph. The backstack tracks navigation history. Each navigation adds to the stack. Back removes from it, press back, the current destination pops. The previous one shows empty stack, the apex sits. Android provides a navigation component. It handles navigation, backstack, arguments, animations, a unified API across fragments and compose. You define a navigation graph, destinations and actions between them. The component manages the rest. Nav controller is the core object. It performs navigation. It tracks the backstack. Nav host displays the current destination. It swaps content as you navigate. In Compose, use navhost to set up navigation. Navhost, navcontroller equals navcontroller, start destination equals home, brace composable, home screen composable, detail screen close brace. Each composable call registers the destination. The route string identifies it. Navigate with navcontroller.navigate details. The navhost shows detail screen. Pop back with navcontroller.popBackstack, or just press the back button. Create nav controller with remember nav controller val nav controller equals remember nav controller. This creates and remembers the controller. Pass it to nav host. Nav host nav controller equals nav controller. Pass it to screens that need to navigate, or better, pass only lambda callbacks. Do not pass nav controller deep into the hierarchy. Pass navigation actions as lambdas instead. Screens often need data. Show details for item 42. Load user with ID ABC. Define arguments in the route. Composable details / item ID type equals navtype.intType. The route includes a placeholder. Navigate with the argument navcontroller.navigate with the argument. Navcontroller.navigate with the argument. ID details /42. Access in the destination backstack entity.item ID. Arguments pass data between destinations. Required or optional. Typed. A user list navigating to user details. Navhost brace composable users user list screen on user list idea list screen on user click equals brace user ID arrow navcontroller dot navigate users / user ID close brace composable users / user ID entry arrow val id equals entry dot arguments. User detail screen idea list screen ID idea list. Brace close brace. User clicks an item, navigated the detail screen extracts and uses it. This is a common pattern. List to detail navigation with past identifier. The backstack is a stack of destinations. Navigate adds to the stack that pop backstack removes. Sometimes you want special behavior. Navigate but clear history. Navigate and replace current. Navigate and replace current. Navigate home brace pop-up to home inclusive equals true close brace. This clears back to home then navigates to home. Useful for login completion. Launch single top equals true prevents duplicate destinations. Navigate to A when already on A does nothing. Keep navigation logic at a high level. Screens should not know about routes. They receive callbacks. User list screen on user click : int arrow unit. The screen calls on user click with the ID. The host composes with navigation. On user click equals brace nav controller dot navigate user / it close brace. This separates screens from navigation. Screens are reusable. Navigation is centralized. Let us summarize. Navigation moves between destinations through a navigation graph. Nav controller handles navigation and backstack management. Navhost in Compose displays the current destination. Pass arguments through routes for data like IDs. Manage backstack with pop-up to and launch single top. Keep screens decoupled from navigation by using callbacks. ViewModel UI state needs to survive configuration changes. It needs a home outside the activity or composable. ViewModel provides that home. Today we understand how ViewModel works and how to use it effectively. Configuration changes destroy activities. Rotate the phone, the activity is destroyed and recreated. Your data gone. User was filling a form, text lost. You can save state in bundles, but that is limited. Only small data, only primitives and parcelables. UI-related data needs to survive. Loading states, fetched lists, user inputs, but it should not persist forever. ViewModel holds UI state that survives configuration changes but is cleared when the user leaves the screen. A ViewModel outlives its activity or fragment. Create an activity, get a ViewModel. Rotate, activity dies, new activity gets the same ViewModel. The ViewModel lives as long as its scope. For an activity, until finish is called or back is pressed. When the scope ends, uncleared is called. Clean up resources there. The ViewModel is not destroyed on configuration changes. It holds state across rotations, language changes, dark mode switches. Extend the ViewModel class. Class myViewModel : ViewModel. Add properties to hold state. Add functions to modify state. In activity or fragment, get the ViewModel with ViewModels. Private val ViewModels. Private val ViewModel : myViewModel by ViewModels. This provides the same instance across configuration changes. First access creates subsequent accesses return existing. In Compose, use ViewModel function. At composable fun myscreen ViewModel : myViewModel equals ViewModel, gets or creates the ViewModel. The ViewModel is scoped to the navigation destination or activity. Same ViewModel across recompositions. Access state from ViewModel across recompositions. Access state from ViewModel, call functions on ViewModel. The composable reacts to state changes. Val UI state by ViewModel. UI state that collect as state. Collect flow as compose state. Use state flow to expose state from ViewModel. Private val underscore UI state equals mutable state flow initial value, mutable for internal updates. Val UI state state flow equals underscore UI state. Expose as read only, update with underscore UI state dot value equals new state, or use update function. State flow is perfect for UI state. It always has a value. It emits to new collectors immediately. It works with Compose. ViewModel provides ViewModel scope. ViewModel scope is a coroutine scope tied to the ViewModel lifecycle. Launch coroutines in ViewModel scope. They cancel automatically when ViewModel is cleared. ViewModel scope.launch brace fetch data close brace. Safe lifecycle aware. Use ViewModel scope for network calls, database operations, any async work triggered by the UI. No manual cancellation needed. When the user leaves, coroutines cancel. ViewModel receives user actions and updates state. User clicks a button. Composable calls ViewModel.onButton click. ViewModel handles the action. Fetches data, updates state, state changes. Flow emits. Composable recomposes with new state. This is unidirectional data flow. Actions go up, state flows down. Clear, predictable. A counter ViewModel class. Counter ViewModel : ViewModel brace private val underscore count equals mutable state flow 0 val count equals underscore count fun increment brace underscore count the value plus close brace causable val count by ViewModel.count.collect the state count by ViewModel.increment UModel holds state composable displays actions modify state. UI reflects changes, survives rotation, cleared when screen exits. Let us summarize. ViewModel holds UI state that survives configuration changes. Its lifecycle outlives activities. It is cleared when the scope ends. Use state flow to expose observable state. Use ViewModel scope for lifecycle-aware coroutines. In Compose, use ViewModel function to get the ViewModel. ViewModel enables clean separation between UI and state management. Repository pattern. Where does data come from? Network, database, cache. The UI should not care. A repository abstracts data sources. Today we understand the repository pattern and how it fits in Android architecture. A repository provides data to the application. It hides where data comes from. Network, database, in-memory cache. The caller just asks for data. The view model calls repository.getUsers. It gets users. It does not know if they came from network or cache. This abstraction is powerful. Change the data source. The caller does not change. Just with fake data, the caller does not change. Repository is the boundary between data and domain. Separation of concerns. View model manages UI state. Repository manages data. Each has one job. Testability. Replace the repository with a fake in tests. No network needed. No database needed. Fast, reliable tests. Flexibility. Start with network only. Add caching later. The view models not change. Single responsibility. Data fetching and logic in one place. A repository can combine multiple data sources. Network for fresh data. Database for persistence. Cache for speed. But there is one source of truth. Usually, the database. Fetch from network, store in database. UI reads from database. UI reads from database. The database is the source of truth. Why? Network is unreliable. Cache can be stale. Database is the reliable source. UI observes the database. Network updates the database. UI sees updates. Define a repository as an interface. Interface user repository brace. Suspend fun get users : list of user suspend fun get user ID int : user fun observe user : flow of list of user calls brace. The interface declares what data is available, not how it is fetched. Implementations can vary. Network user repository, fake user repository, forget user repository, fake user repository. Depend on the interface, not the implementation. This enables flexibility and testing. Repository functions are often suspend functions. Suspend fun get users : list of user. Fetching data takes time. Suspension makes it non-blocking. For one-time requests, use suspend functions. Fetch user by ID, create a new item, delete. For observable data, return flow, fun observe users : flow of list of user. UI collects, receives updates. The repository handles the async nature of data fetching. Callers use suspend or collect. A simple repository implementation. Class, user repository implot to constructor, API, user API, DAO, user API, DAO : user repository. Get users, try to fetch from network, store in database, return from database, fallback if network fails, return cache data from database. The implementation decides the strategy. The interface stays simple. More complex strategies are possible. Check cache age. Fetch in background. Sync periodically. Cache first. Check cache. Return if valid. Otherwise, fetch. Network first. Always fetch. Update cache. Stale while revalidate. Return cache immediately. Fetch in background. Update when ready. Offline first. Always return cache. Sync when possible. Choose based on your needs. Freshness requirements. Offline support. Performance. The repository encapsulates the strategy. Callers are unaware. Repository sits between model and data sources. UI talks to ViewModel. ViewModel talks to repository. Repository talks to API and database. Dependencies point inward. Repository does not know about ViewModel. API does not know about repository. This layering makes each component testable and replaceable. Compound, compose to ViewModel to repository to data sources. Let us summarize. Repository abstracts data sources from the rest of the app. It provides a clean API. Callers do not know where data comes from. Single source of truth keeps data consistent. Use suspend functions for one-time operations. Use Flow for observable data. Repositories enable testing, flexibility, and separation of concerns. Define interface, implement with real sources, test with fakes. Room database. Apps need to persist data locally. User preferences, cached content, offline data. SQLite is the standard solution on Android, but raw SQL is tedious. Room provides a clean abstraction. Today we learn how to use Room for local persistence. Room is a persistence library of a SQLite. It provides compile time verification of SQL queries. Catch errors at build time, not runtime. Room reduces boilerplate, no cursor management, no manual serialization, just annotate classes and write queries. Room integrates with Coroutines and Flow. Suspend functions for queries, Flow for reactive updates. Room handles the SQLite details. You work with objects and type-safe queries. Room has three key components. Entity is a table, a data class annotated with @entity. Each instance is a row. DAO is data access object. An interface annotated with @DAO. Contains methods for database operations. Database is the database holder. An abstract class annotated with @database provides DAO. An abstract class annotated with @database provides DAO annotated with ties them together. An entity is a data class representing a table. @entity data class user @primary key val id :int val name :string val email :string. The annotation marks it as a table. The primary key uniquely identifies rows. Column names default to property names. Customize with @columninfo @columninfo name equals user 90 val name. Column in string val name user 90 name :string. The column is named user. Add indices for faster queries. @entity indices equals index email unique equals true. A DAO is an interface with query methods. A DAO interface user DAO @query ck star from user suspend fun get all :list of user @query takes a SQL string. Room verifies it at compile time. Insert, update, delete have dedicated annotations. Insert suspend fun insert user :user @update suspend fun delete user :user. On conflict strategy handles conflicts. Replace replaces existing. Ignores new. The database class ties everything together. @database entities equals user version equals one abstract class. App database room database abstract fun user DAO user DAO. List entities in the annotation. Specify schema version. Abstract functions expose DAOs. Room generates the implementation. Build with room.database builder. Pass context, database class, and name. Room.database builder context app database.build. DAO methods can be suspend functions. Suspend fun get all :list of user. The query runs off the main thread automatically. Room handles thread switching. You just call the suspend function. Room moves work to background. For inserts and updates too. Suspend fun insert user :user. Non-blocking database access. No manual thread management. No async task, just coroutines. For reactive updates, return flow fun observe all: flow of list of user. No suspend needed. Returns immediately. When database changes, flow emits new data. Insert a user. Observers get updated list. @query star from user. Fun observe all: flow of list of user. Room monitors the table. Any change triggers emission. UI stays in sync. UI observes database via. Schema changes require migrations. Version 1 has user. Version 2 adds a column. Room needs instructions. Val migrations q2 equals migration 1 to override fun, migrate database brace database.sexquel alter table user adt column age indeg close brace. Add migration when building. Add migrations z_squel. Without migration, data is lost. Room recreates the database. Plan migrations early. Version schema evolution. Let us summarize. Room abstracts SQLite with compile time verification. Entity is a table. DAO has query methods. Database provides DAOs. Use suspend functions for one-time queries. Use flow for reactive, observable queries. Handle schema changes with migrations. Room makes local persistence clean, safe, and reactive. Network requests. Most apps fetch data from the internet. User profiles from a server, products from an API, news from a feed. Today we learn how to make network requests in Android using Retrofit and Coroutines. Apps communicate with servers over HTTP. HTTP requests have a method. Jet retrieves data. Post sends data. Pip updates. Delete removes. Requests go to a URL. HTTP6 API example com users. The server processes and returns a response. Responses have a status code. 200 is success. 404 is not found. 500 is server error. Response body contains data, often JSON format. Retrofit is the standard library for HTTP in Android. You define an interface describing the API. Retrofit generates the implementation. No manual HTTP connection code. No passing JSON manually. Retrofit handles it. Retrofit works with coroutines, suspend functions for requests, non-blocking calls. Retrofit works with various serialization libraries. We use Kotlin X.serialization. Describe your API as an interface. Interface user AP at Jet users. Suspend fun get user list of user the two at Jet G user / user ID. Suspend fun get user at path user ID int user the two at Jet et at post at put at delete mark the HTTP method. The string is the path. The combined with base URL at return type is passed from JSON. Suspend makes it non-blocking. Create a retrofit instance. Retrofit.builder.base.ai squads API example com.add converter factory.build. Base URL is the server address. All paths are relative to it. Converter factory handles serialization. We use Kotlin X.serialization converter. Creates the API implementation. Retrofit.creates URL by class Java. One retrofit instance base URL. API methods are suspend functions. Val users equals user API.getUsers. This suspends until the response arrives. Call from a coroutine. ViewModel scope.launch brace val users equals API.getUsers close brace. Network I/O happens automatically on background thread. Retrofit handles it. No callback hell. No Rx Java complexity. Just sequential code that suspends. Errors throw exceptions. Wrap in try catch or use result type. Retrofit can response wrapper. Suspend fun get user id it response of user da2. Check if successful. If response dot is successful brace response dot body close brace. Access status code response dot body close brace. Access status code response dot code. Access error body. For simple cases return the type directly. Retrofit throws on nom2xx. For complex error handling, return response and check manually. Network calls can fail in many ways. Network unavailable, server unreachable, timeout, server returns error, wrap calls and try catch, catch IO exception for network errors, catch HTTP errors try brace API.getUsers close brace catch EIO exception brace TPI.getUsers close brace server error close brace catch EIO exception brace server show appropriate messages to users. Retry options. Offline fallback. Kotlinks.serialization parses JSON. Mark data classes with @serializable. @serializable data class user the two val id int val name string. Property names map to JSON keys. Customize with @serial name idcs nidcs name user type name val name string.json keys user name. Bold values handle optional fields. Val age :int equals 0, missing int equals. Add the converter to Retrofit. Add converter factory Kotlin's serialization converter. Let us summarize. HTTP is the protocol. Get, post, put, delete are common methods. Retrofit generates API implementations from interfaces. Suspend functions make network calls non-blocking, handle responses and errors appropriately. Kotlin's.serialization passes JSON with annotated data classes. Network requests are foundational for connected apps. Dependency injection. Classes depend on other classes. A ViewModel needs a repository needs an API and a database. How do you provide these dependency? Dependency injection is the answer. Today we understand DI and how to use Hilt in Android. Classes create the dependencies internally. Class user ViewModel brace val repository equals user repository close brace. The ViewModel creates its own repository. Tight coupling. Hard to change. What if you want a different repository? What if you want to test with a fake? You cannot. The ViewModel controls the dependencies. This makes code rigid. Changes ripple through. Testing requires real implementations. With DI, dependencies are provided from outside. Class user ViewModel repository user repository brace use repository close brace. The constructor receives the repository. The ViewModel does not create it. Someone else provides it. This inverts control. The class says what it needs. Something else provides it. Now you can provide different implementations, real for production, fake for testing. The class does not change. Testability. Pass fake dependencies in tests. No network, no database needed. Fast, isolated tests. Modularity, swap implementations without changing dependent code. Different database for debug builds. Single responsibility. Classes focus on their job, not on creating dependencies. Configuration centralized. One place decides what implementations to use, not scattered across classes. You can do DI manually, pass dependencies through constructors, create them at the top level, wire everything together. This works for small apps. It becomes tedious for large apps. Many dependencies, many layers. DI frameworks automate the wiring. Hilt for Android, Dagger under the hood. You declare what you need. The framework provides it. Automatic, type safe. Hilt is the recommended DI framework for Android. Add Hilt plugin and dependencies. Annotate your application class. Add Hilt Android app class my application application. Annotate activities and fragments. Add Android entry point class main activity. Inject dependencies at Android entry point class main activity. Inject dependencies at inject latent var repository. Hilt provides the imlep. Tell Hilt how to create objects. Constructor injection is simplest at inject constructor on the class. Class user repository at inject constructor. Private val API user AP. Private val DAO user DAO. Hilt sees at inject and knows how to create it. For interfaces or classes you do not own, use modules. At module at installed in singleton component class appodule at provides fun, provide retrofit retrofit at provides tells Hilt how to create the object. Scopes control object lifetime. At singleton leaves for the app lifetime. One instance shared everywhere. At ViewModel scoped leaves for the ViewModel lifetime. Per ViewModel instance. At activity scoped leaves for the activity lifetime. New instance per activity. Use at singleton for shared resources. Retrofit database. Use at ViewModel scoped for per screen data. No scope annotation means new instance each time. Be intentional about scopes. ViewModels need special handling. At Hilt ViewModel class user ViewModel at inject constructor repository user repository ViewModel. At Hilt ViewModel marks it for Hilt injection. At inject, constructor receives dependencies. Hilt provides them. In composable, use Hilt ViewModel. At composable, fun user screen ViewModel. Kotlin user ViewModel equals Hilt model. Hilt creates the ViewModel with all its dependencies. Let us summarize. Dependency injection provides dependencies from outside. Benefits: testability, modularity, single responsibility. Hilt automates dependency wiring in Android. Use at inject for constructor injection. Use at provides for modules. Scopes control lifetime, singleton, ViewModel scoped, activity scoped. At Hilt ViewModel enables ViewModel injection. DI makes large apps manageable and testable. Testing on Android. Code should work correctly. Tests verify that it does. We have learned to build apps. Now we learn to test them. Today we explore testing strategies for Android applications. Tests catch bugs before users do. They give confidence to refactor. Change code, run tests. If they pass, you did not break anything. Tests document behavior. Reading tests shows how code should work. Tests save time. Manual testing is slow. Automated tests run in seconds. Tests are especially important in Android. Many devices, many OS versions, you cannot manually test everything. Unit tests run on your computer. Fast, no device needed. They test small units of code, a function, a class, isolated from Android framework. Instrumented tests run on a device or emulator. Slower, need Android environment. They test code that interacts with Android. UI components, database operations, real device behavior. Start with unit tests. They are fast and cheap. Add instrumented tests for Android-specific code. View models are ideal for unit testing. They contain logic. They transform data. They do not touch Android UI directly. Create a view model with fake dependencies. Call methods, assert state, class users view model test, at test fun load users update state view model dot users at equals expected view model dot UI state dot value, mock or fake the repository. Control what data it returns. Test view model behavior. Coroutines need special handling in tests. Use run test instead of run blocking. It handles virtual time. Tests do not wait for delays. Run test brace val view model equals view model dot load data advance until idle assert equals expected view model dot state close brace advance until idle runs all pending coroutines. No waiting. Use test dispatcher for controlled execution. Replace dispatchers in tests. Standard coroutine testing tools make async code testable. Test doubles, replace real dependencies. A fake is a working implementation for tests. Fake user repository stores data in memory. It behaves like a real repository. Class fake user repository colon. User repository private val users equals mutable list of override. Suspend fun get users equals mutable list of override. Suspend fun get users equals users. A mock records interactions. You verify methods were called. Fakes are often better. They test behavior, not implementation details. Tests are less brittle. Compose has a testing library. Use create compose rule to set up tests. At get rule val compose tests rule equals create compose rule. Set content and interact. Compose test rule dot set content brace my composable close brace. Find elements with matches on node with text submit dot perform click. Assert state on node with text submit dot perform click. Assert state on node with text submit assert is blade. Compose tests verify UI renders correctly and responds to interaction. Test pyramid. Many unit tests. Fewer integration tests. Even fewer UI tests. Unit tests are fast and focused. Test logic in isolation. Integration tests verify components work together. View model with repository. UI tests verify the whole screen works. Slower but important. Cover critical paths with UI tests. Balance coverage with speedway. Fast feedback, it's feedwild. Test behavior. not implementation. Focus on inputs and outputs. Keep tests independent. Each test sets up its own state. Name tests clearly. Should show error when network fails. Test edge cases, empty lists, error states, boundary values. Run tests often. After each change. Catch regressions early. Make tests deterministic. No random data. No time dependence. Let us summarize. Unit tests run fast, no device needed. Instrumented tests verify Android behavior. Test view models with fake dependencies. Use run test for coroutine testing. Fakes often work better than mocks. Compose UI can be tested with Compose test rule. Follow the test pyramid. Many unit tests, fewer UI tests. Testing builds confidence in your code.